convergence of power series. Yeah. So the basic results, but we need to apply it. Yeah. Because when we take derivatives, we need to make sure, all the x values selected must be inside the convergence interval. Yeah. So let's look at how to calculate. My remote control. All right. Yeah. Yeah. So that partial sum and the remainder of power series. Yes. First, let me give you the basic method people use to study the convergence of power series. Yeah. This partial sum, typical way people use to study the convergence. So what's that? All right. So given this is a general power series. Yeah. Here we choose the simpler version. So this is the simpler version. Yeah. Special x0. For this simpler version, the infinite sum, it's relatively hard to study, right? The convergence. Yeah. Relatively hard to study. Then we define partial sum. Yeah. The sum of first, you can say n plus 1 terms. N plus 1 terms. Yeah. We call it nth partial sum. The highest degree, the term with the highest degree, yeah, nth degree. Order, because we know order degree, the meaning is different. Yeah, so here when we choose the word, we need to be careful. Yeah. All right. Yeah, for the simpler version. The good thing about, if you want to ask why we use this partial sum method, because each partial sum is well defined, right? Yeah. The definition, because it's a finite sum. Finite sum, when you plug in x value, you can always get a valid number. Yeah. Because for infinite sum, you don't know. Yeah. So that's why people use the partial sum. Yeah. Every time when you take partial sum, you get some value. Yeah. All right. But the question is, how do we use the partial sum, a sequence of partial sums, to study the convergence of the the power series? Yeah. All right. Then, after you take the partial sum, then you have a remainder part. Yeah. So you also need to, the tail part. After you cut off the remainder, that tail, long tail, you need to collect. You put it in the remainder function. You can study. Yeah. All right. Yeah. All right. So then, a general power series we can write as a sum of two parts. Yeah. The partial sum part and the remainder part. Yeah. Yeah. All right. Then convergence. Yeah. After this notation, yeah, set up. Let's consider the convergence question. Yeah. What's the benefit? New representation. Yeah. Now, when we study a power series, we change our view slightly. Yeah. Because this new representation allows us to change our view slightly. So what kind of view? Yeah. Our old view, infinite sum, summation with infinite many terms. That's the old view. Yeah. So the new view becomes, we change in this way. We study the sequence. Yeah. So here you can see we study a sequence with infinite many terms, yeah, items, yeah, infinite many, yeah. But each one is well defined, right? Yeah. Each one is a valid number. Yeah, so it becomes, so you study one infinite sum object. You change to, you study the convergence of this sequence with infinite many terms. Yeah. Yeah. At least here, each term is well defined. Yeah. But the sequence may not be convergent. The sequence may not be convergent. Yeah. Yeah. So here you can see if the sequence does not converge, then the original power series does not converge. If the original power series converges, then this sequence also converges. Yeah. But we just changed the view. Yeah. But this new view a little more convenient when we study sequence convergence in calculus. Yeah. So we study sequence convergence first. Yeah. So we have many theorems we can use for the sequence convergence. Yeah. All right. Does the summation? Yeah. So next, yeah, we look at the convergence. One example. Look at this geometric series. So we're familiar with this geometric series, right? Yeah. This geometric series, you can see this. You look at the summation part. If you plug in x equals 1, it does not converge. X equals 1. It diverges. Yeah. So the convergence interval must be absolute value of x strictly less than 1. That's the convergence interval. Yeah. Okay. Yeah. If it is if this geometric series converges, then it equals 1 over 1 minus x. Yeah. Otherwise, it does not equal. Okay. Yeah. Only under the condition it converges, or x selected within the convergence interval, then you can apply this formula to calculate the summation. 1 over 1 minus x, as a simple example. All right. Then the convergence interval of power, how to calculate convergence interval. Yeah. All right. Yeah, so we consider the sequence convergence. Yeah. All right. Yeah. So here we consider at each point, yeah, x1. So here we select some point, yeah, x1. Yeah. Because think about why we select a special point at x1. Think about, if you do not select a point, each little s is a function, right? Is a function. Yeah. How do you study convergence of a sequence of functions? Yeah. Sequence of functions. Yeah. So that's a little hard. Yeah. So when you study the convergence of a sequence of functions, yeah, so you want to study, for each function, you only look at one specific value. Yeah. Because this value, x1, could be selected in an arbitrary way. So you don't worry, you can select any point, yeah, in the domain. Yeah. All right. So let's consider at x1. So we want to, we expect, yeah, here, convergence, right? Convergence. So this sequence at x1 point, we want to see it converges. It converges, so we imagine it converges to some imaginary function s. Yeah, because this little s is not, we haven't defined little s, right? Yeah, you can see so far we didn't define what is that little s. Yeah. So the definition of this little s is when the sequence converges, that value converges at the x1 point. We use that value to define the value of little s at that point. That's our definition. Yeah. Yeah. But we need the convergence of that sequence first. Yeah. If the sequence diverges, then we cannot define this little s. Yeah. But if the sequence converges, then there is a limit. We use that limit to define this new function little s. Okay? Yeah. So that's the logic. Yeah. So little then s1, if we go back to our power series representation, yeah, that's the same as when you plug in x with the value x1, yeah, so you get the same thing. Yeah. All right. So here, mainly the notation thing. Yeah. People change notation. Yeah. Yeah. All right. Then let's consider the radius of convergence. Yeah. Yeah. All right. Here, there are two formulas. Yeah. A formula, B formula, both correct. Okay? A formula, the convergence radius r equals 1 over the limit of nth root, yeah, of absolute value of am coefficient. Yeah, nth root. Yeah, actually, yeah, yeah. So here, this is a simpler version. Yeah, so there is a more general version. Yeah, here we choose the simpler version. Yeah, because the more general version will be more rigorous. The simpler version here, you can see if the bottom, think about if, because yeah, so the limit, so there is you need to consider if the limit exists or not, right? Yeah, you need to consider if the limit exists or not. So there is that issue. Okay, yeah, but so with that more general version, you know, it is guaranteed the limit always exists. Yeah, yeah. But that general version, we need to introduce some advanced concept. Yeah. So for that reason, so here we want to get around. Yeah. So let's just take this simpler version. Yeah. All right. The second formula, equivalent. You can use the first formula, you can derive second one. Second one, you can derive the first one. These two equivalent. Yeah. But sometimes the first formula is easier to use. Sometimes the second formula easier to use. Yeah. So when we use, so we want to see, so which one is better for our current question. Yeah. All right. So later, I will apply these formulas to calculate. Remember the last time, when we solve the Legendre equation, remember Legendre equation? So we found the solution y1, y2, right? y1, y2. At the end, we saw that convergence interval, but we don't know how to get it. Yeah. Later, I will show you how to get that convergence interval by these two formulas. Yeah. All right. Yeah, so as an example, yeah, the power series representation of e to the x exponential function, yeah, so you can apply that here. The second formula, yeah, after simplification, yeah, yeah. So the limit goes to 0, but your r is 1 over that limit. That means r is infinity. R infinity, that means the interval is the whole real axis. Whole real axis, everywhere. So for this power series, you can plug in any x, it converges. Yeah. 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 Extremely large x, yeah, 1 million, 1 billion, it also converges. Okay? You plug in 1 billion, okay, plug in, still converges. Yeah. That's the nice property of this exponential function. Okay? Yeah. Yeah. All right. The second example, yeah, the geometric series. Yeah. This time you can see when we apply the second formula for the calculation, yeah, r equals 1. If you apply the first formula, it's still okay, right? Yeah, because am equals 1, yeah, 1 takes m through, still also 1. Yeah. First formula, also very easy. Yeah. All right. Next, yeah, this one. This one you can see m factorial. Yeah, for each term, the coefficient m factorial. Yeah. So then you take your second formula, it's m plus 1, but m goes to infinity, right? M goes to infinity, then 1 over infinity is 0. If the r equals 0, then it diverges. Yeah. Yeah. Any x you plug in, any x other than 0, you plug in 0, it converges, right? Yeah. But when we look at the, convergence interval, yeah, so we do not use the 0 point, okay? Yeah. So we use the point other than the 0, it diverges. Yeah. So here you can see, yeah, all these cases could happen, okay? Yeah. Oh, yeah. All right. So that's this result. Yeah. Radius of convergence concept. Yeah. Then now I want to apply one of the formulas to calculate, to check our previous result. Convergence interval for the Legendre's power theory. Yeah. There are 2 power series. Okay? Yeah. So we find 2 solutions, 2 power series solutions for the Legendre equation, but yeah, remember one of the 2 based on n. Yeah, n here, n is a parameter. Okay, n is a given parameter. Yeah, fixed. That n given is a fixed number. Yeah, it must be an integer, but it must be fixed. Yeah, and when n is an even number, y1 is a polynomial. When n is an odd number, y2 is a polynomial. Okay? But if y2 is a polynomial, y1 is a power series. If y1 is a polynomial, but y2 is a power series. Yeah. So that's the current situation. Yeah. So last time we saw the radius of the convergence is 1. Right? But the question, how do we see it? Right? Yeah. After we have those 2 formulas, now let's apply those 2 formulas to check. Yeah. So these 2 formulas. Yeah. And usually, for this situation, usually the second formula is relatively easier to use than the first one. First one, you take nth root. Yeah. It could be very messy, right? It could be very, very messy. The second one, why most of the time the second formula is easier to use? Because you have a lot of cancellation. Yeah. When you use a sub m plus 1 over a sub m, you can cancel out many factors. Here we have the things you can see. Yeah. This coefficient, if you compare with this one, the numerator you add for the leftmost, that factor you add it. The rightmost factor you also add it. The middle part, same as the previous one. Yeah. So then, denominator, you add 2 consecutive numbers in the product, factorial. Okay, 5 factorial, you add two more numbers, 4 and 5. Yeah. All right, so a lot of cancellation. Yeah. All right. Let's just check one of the two. Yeah. Here, that should be enough. One of the two. All right. Yeah. But here I need to, before I apply the formula, I want to do some manipulation to make the summation more friendly for our formula. So here, yeah, because when I look at the convergence of y2 power series, the summation, yeah, there is a common factor x, right? Yeah, I want to take the ratio, yeah, take away that common factor, yeah, because that x does not change the convergence, right? Yeah, because the x should be different from 0. Yeah. When we consider convergence, we consider non-zero x. X cannot be 0. Okay. Yeah. All right. So that's why we divide it by x, both sides. Yeah. So the right-hand side, after we divide it by x, then here, this u, I want to replace x squared by this u, yeah, because the old way there is x squared. Now I want to use a new variable u. Yeah. So now the coefficients, based on that u terms. Yeah. Yeah. Because in that way, if you use x squared, you skip a term, right? Every time you skip a term, then when you apply this formula, you have a chance divided by 0, right? Yeah. That's not friendly. Yeah. That's not friendly. Yeah. The reason, remember, if people ask, yeah, why when you apply this formula, sometimes some terms, the coefficients of some terms could be 0, then you divide it by some 0. Yeah. So that's the reason. So I mentioned that more general formula. That general formula will get around this problem. The simpler version of the formula cannot get around that problem. Okay, so then I do some special manipulation here. I use u variable replace x squared. Then we do not skip terms, right? But convergence is the same, right? Here I do not change the convergence. Okay, yeah, I use u represent x squared. Yeah, still equivalent. These two power series equivalent. Yeah, no change. But after I do the substitution, now you can see we have no problem. We can apply that B formula. Okay? Now let's apply the B formula. Yeah. All right. But we need to find what is the AM, the coefficient. The AM we need to find. Yeah. For the general term, can we represent that AM? Yeah. All right. So this is the general term. You can see. Yeah. 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 All right. Yeah. The denominator 2n plus 1 factorial denominator. Yeah. Numerator, yeah, so based on the rule. So we need to do multiplication. Yeah. So this is the middle line. Then we do, multiplication n plus 2, n plus 4, yeah, in that way. Yeah. Left hand side, n minus 1, n minus 3. Yeah. In that way. Yeah. That's the general term. Okay, all right. Then m plus 1, yeah, based on that, m plus 1. So here, for each m, we need to replace m by m plus 1, right? Replace m by m plus 1. Then the factorial, you have 2m plus 3 factorial. Yeah, you plus 2. Yeah. m plus 1, so 2 times 1. So 1 plus 2, you get a 3. So 2m plus 3. Yeah. Then the numerator, yeah, so the rightmost factor, you add 2. You multiply another factor, yeah, another following factor. Okay, yeah. The leftmost, you need to go one more number to the left. Yeah, that's the structure. Then you take a ratio. Absolute value, you take a ratio. After cancellation, you have this number. Yeah. Numerator, you have two factors, product of two factors, denominator product of also two factors. Yeah. But when m goes to infinity, yeah, because all these numbers relatively small, right? The minor part, can be ignored, right? Yeah, because m becomes very, very large. All these minor terms, can be ignored. Then you do cancellation, 2m cancel out, you get a 1. You get a 1. Yeah. So you can easily see the limit is 1. Yeah. Yeah. Another way, if you cannot see in this way, if you have experience, you can do it this way. But some students, if you still feel hard, you just do division by 2m times 2m squared, both the numerator and the denominator. You do division. Yeah. If you do that division, the first factor becomes 1 plus 1 minus n over 2m. The second, 1 plus 2 plus m over 2m. The bottom, 1 plus 2 over 2m. 1 plus 3 over 2m. All these terms go to 0. Yeah, because m goes to infinity, right? All these things, fractions goes to 0. Goes to 0. Yeah. Then you just 1 times 1 over 1 times 1. That's 1. Yeah. So that's the way. Yeah. So if you really want to rigorously see it, then you do that way. So that's the common way people use. Yeah. Otherwise, if we have a lot of experience, so we know those minor terms can be ignored. Yeah. So then we can see quickly. Yeah. All right. Lucas.
Let's step back and look at I'm confused on how we find m and m plus 1.
M plus, m plus 1, do you mean this one?
Yeah, I'm
Cover?
just both. Is it just going through, I don't understand how we find the
General term?
Yeah.
How to see the general term? Yeah, by our observation. Okay? All right. Yeah. So here, we need to find the rule. The exponent of u is, when it's 1, it's 3. Yeah. Can you see it's 2 times 1 plus 1 by your observation? Okay? Here, exponent number is 2. Here, 5. Can you see 2 times 2 plus 1? Yeah, so that's you get a denominator. The numerator, you also need to find, because when you see some term, every time, starting from 2, always even number, consecutive even integer, but the last one is 2 times the exponent number. Yeah. Use your eyes, do observation.
Okay,
Yeah.
So, all right.
Yeah.
That makes sense.
Right. Yeah. For all things like this, people, so you make, you look at the terms, you try to compare. Yeah. What's the relationship? Okay. Yeah. Here. Yeah. When I do it, so I use that way. Okay. So what's the rule? Yeah. But you need to look at a few terms. Yeah. Here, probably 2 terms enough. Yeah. Yeah. If not enough, you need to get third term. Okay. Third term, then you try to find the rules. Yeah. Yeah. So, right. So that's the weight, the typical way. Yeah. All right. Yeah. Now, so after that, we answer this question. Yeah. Convergence interval, that question. Yeah. All right. So let's go to the next topic. Yeah. Next topic, existence of power series solutions. Yeah. some theorem, existence theorem. Yeah. Yeah. Because if you know the existence theorem, you have the confidence, right? Yeah. So when you see a given ODE, yeah, if it follows certain conditions, then you know there must be a power series solution. Yeah? Yeah. All right, let's look at the theorem. Yeah. Here we study the ODE, second order ODE, with this form. Okay? Yeah. Yeah. So we are familiar with this form. Yeah. All right. But here we need to have a concept, analytic function. Yeah, last time I mentioned that C infinity, right? You can take derivative, you know, infinite many derivatives, analytic function. Yeah, but here it uses a different way to define that analytic function. Yeah, a function f of x is called analytic at a point x equals x0 if it can be represented by a power series in powers of x minus x0 with positive radius of convergence. Yeah. So that's from another angle people define the power series. Because if this condition is satisfied, then you can take infinite many derivatives on this function. Yeah. Because when you take the infinite many derivatives on this function inside the convergence interval, all those derivatives, the power series corresponding to all those derivatives, all converge. All converge. Yeah. So that's why you can take infinite many derivatives. Yeah. So another way, yeah, so you can define analytic functions. Yeah. All right. With this function definition, then we have the existence of power series solutions. PQR, all these three functions in equation 12 are analytic at x equals x0. Yeah. Then solution of equation 12 is analytic. Yeah, its solution also analytic. Okay, yeah, and thus can thus be represented by power series in powers of x minus x with positive convergence radius. Yeah, r positive number. Yeah, not zero. Yeah, yeah, that's the existence of power series solutions. Yeah. All right. Yeah. Yeah. But if we want to get a little more details, because for each function, although we know they are analytic, but their convergence radius, in general, different. Yeah. So here we assume the radius of convergence for P function, capital R1, for Q function, capital R2, for R function, capital R3. Yeah? So all three different radius. Then the solution, the radius for the solution should be the minimum of these three numbers. Yeah. Because we want X falls into all the three convergence intervals, then you have to take the smallest convergence radius. Yeah. Radius of convergence, the smallest one. Yeah. Then you can guarantee X falls into all three convergence intervals. Yeah. That's simple. All right? Yeah. Yeah. So with this existence theorem, then when you are given a second order ODE, yeah, so here we just consider second order ODE. Yeah. Although this method can be extended to higher order ODE, yeah, but it could be too complicated. Yeah. So here we just look at the second order case. Yeah. Operations on power series. Then after that, after we study the convergence, then we need to do the calculation. Yeah. We need to do calculation on power series. So we need some basic properties. Yeah. So operations. Yeah. Here there are several basic operations. Yeah. The power series. Yeah. We assume we have two power series. Now we want to do operations between two power series. All right. And we assume the radius of convergence are positive. Yeah. All right. Now, the first property, term-wise differentiation. When we take a derivative, we take term-wise derivative. Yeah. All right. So you take like this, and it's true within the convergence interval. Within the convergence interval. It's true. Yeah. Yeah. Inside the convergence interval, you can do this. Yeah. Okay? Yeah. That's the first property. All right. Yeah. The same convergence interval. See? Right? We do not shrink. Okay? So here, you do not need to shrink the convergence interval. You just use the same convergence interval. Okay? Yeah. That's the first property. Second property, term-wise addition. When you want to add two power series, you just do the, term-wise addition. Yeah, straightforward. Yeah. The same convergence interval also, right? Yeah. Yeah. So here. The third one, term-wise multiplication. Multiplication, a little harder. Yeah. So the formula, a little more complicated. Yeah. Then, each term you can write in this way. Yeah. You can try to find the rules. Yeah. Okay. Yeah. First A coefficient, the last B coefficient. Yeah. Because you need to look at the degree. Yeah. Degree is m. The total degree is m. Okay. Yeah. Yeah. So then, you can see the sum of the two subscripts, m. 1 plus m minus 1. The sum of two subscripts equals that degree number, m. Yeah. So you add up, all those possible products. Yeah. Yeah. So that's the term-wise multiplication. Yeah. A little harder, yeah, but you have this formula. Yeah. All right. The fourth one, vanishing of all coefficients. When you compare one power series equal to 0, yeah. So if you know one power series equals 0, then you can say all the coefficients must be 0. Yeah? Yeah. Yeah. So that's when we try to derive the recurrence formula, yeah, we use this property, yeah, vanishing of all coefficients. Yeah. All right? Yeah. So that after this slide, then when you work on your power series questions, so you can feel very comfortable, yeah, because we apply these properties. Yeah. Yeah. And usually most of the time we use property number 1, 2, and 4. Yeah. Only in some special situation we need to apply property number 3. Yeah, that's a relatively hard one. Yeah, so this is the relatively hard one. Yeah. Okay. Yeah. Property number 3. Yeah. All right. Yeah. Yeah. So then, yeah, remember this weekend I need to give you the homework assignment number 3. Yeah. Together with quiz number 5. Yeah. Quiz number 5 is part A of homework assignment number 3. Yeah, part A, part B. Yeah. So the quiz A, then I only give you part B. Yeah. After quiz A, I give you part B. Yeah. Quiz A, due date the end of next Sunday. Yeah. But quiz part B, I'll give you a few more days. Yeah. After the due date of quiz 5, you still have, 3 more days. 3 more days Wednesday after Sunday. That's the due date of part B. Yeah. Yeah. All right. Yeah. So that's the, here. All right. Next, we need to do B.5 examples using Frobenius method. Yeah. Okay. All right. Yeah. First, let us review a little bit. Yeah. Probably you couldn't remember. So what is the Frobenius method, right? Yeah. So let us review a little bit. Yeah. So let me jump to that theorem slide. Yeah. So there are 2 slides about Frobenius method. There are 3 cases: case 1, case 2, case 3. Yeah. Case 1, very simple. Yeah. Case 2 and case 3, a little harder. Yeah. So first, let me get it out and jump to those 2 slides. Yeah. To refresh your memory about this Frobenius method. Okay. Yeah, here, these 2 slides. All right, starting. Yeah, here I do not use the slideshow. Yeah. All right. Frobenius method, basis of solutions, 3 cases. Yeah. Yeah. So we are working on second order ODE. Yeah, like this. Yeah. Remember initial equation. Later, I will, when we do the concrete examples, so I will explain how to get this initial equation. Yeah. If some of you still have question how to get this initial equation, then I will explain. Yeah, when we work on some concrete examples. Yeah. All right. Yeah. Actually, it's pretty straightforward. Yeah. All right. Case 1. Yeah. When you solve this initial equation, you have two roots. Yeah. So here. Real complex. Yeah. So for us, we just consider real roots. Yeah. Complex, too complicated. Yeah. So we consider the real roots. Yeah. All right. Case 1, distinct roots, not differing by an integer. The difference of these 2 roots is not an integer. If it's integer, then that's case number 3. Yeah. Yeah. So it's not an integer, then you can use this way, straightforward way. Yeah, because y1, you just use x to the r1 times an undetermined power series. y2, x to the r2 times another undetermined power series. Then you plug into the original equation, you can find the coefficients of the power series. Yeah. So case 1 is straightforward. Yeah. But case 2 and case 3, then you need to do something special. Yeah. So you cannot use this way. Yeah. So the next slide, case 2. Yeah. Case 2, double root, r1 equals r2 equals r, double root. Yeah. So then, y1, yeah, so x to the r, then times on some undetermined power series. Yeah. So that's the usual way. Yeah. But your y2 has a quite different form. Yeah. So your y2 has a special term that is y1 times natural log of x. Yeah. After this term, then you have the remaining part, x to the r times a power series, but this power series is a special one, a1 times x plus a2 times x. There is no a0 term. See? Yeah. Yeah. So you need to use this assumption. Then you determine the second power series. So that's for the y2. Okay, all right. Then case 3, roots differing by an integer. Yeah, I1, I2 two roots. You take the difference. This time the difference happens to be an integer. So now you should use this case 3 to get a second. Yeah, the first, the y1 function, normal, right? Yeah. So for all these cases, when you calculate y1, the same way. Yeah. But the difference is at the y2. When you calculate the y2 function, now the y2 function equals k times. So here I need to draw something. This slide I need to draw something. So I need to write something. Okay, here something, last time I said something is incorrect. So what is this k? This k is an undetermined coefficient. You need to determine it. So it's undetermined coefficient. K may turn out to be 0. So k is allowed to be 0, but after you plug in this k, you need to determine this k. Okay, to be determined, this k. All right, to be determined. Okay, all right. Then after that, extra R2 times the power series. This time you have A0 term, right? Case 3, you have A0 term. Case 2, you don't have A0 term, right? So you can see the difference. But when you calculate case 2 and case 3, here you can see in this way, you can expect you need to do a lot of complicated calculation. You can imagine a lot of complicated calculation. So let me tell you my plan, because I need to ask you to practice these cases. So in your homework number 3, I plan to give you 3 power series questions for these 3 cases. Case 1, 1 question. Case 2, 1 question. And case 3, 1 question. 3. All right. All right. But after the break, when you come back, we will do case 2 and case 3. So I'll give you 2 examples, case 2 and case 3. But the way we are going to do, we will not apply these 2 methods directly, because are based on the textbook examples. In the textbook examples, these 2 ways are not used. Why not used? I will explain. Because there are 2 special cases. We can get around these 2 complicated formulas. So in your homework assignment, I will use the similar examples as in the textbook. Okay? Allow you to get around these 2 complicated formulas. All right? But in the final, I will, because final, I will show you 1 example you cannot get around. You have to use this formula. Okay? So I will use 1 question in the final. So you have to do it. Okay? So you have to, but I try to make the question as simple as possible. You just do 1 question. Okay? In the final, for your power series question, you only need to do 1. Only need to do 1. Okay? But that one, you cannot get around. So you have to use 1. So case 2 and case 3, I will select 1 of the 2. You need to do 1 question. But in the final, okay? Not in our homework assignment number 3. All right, let's take a break. After you come back, then we study those 2 examples. Case 2, case 3, 2 examples.
We get 2 hours on the final?
Yes. 2 hours in the final. Even that, think about. When you have 10 questions, although I can control the difficulty of the questions, think about, even you have 2 hours, still very hard, right? 10 questions. But so I will, I will do some way. Yeah. In 2 hours, you do as much as you can. Okay? Yeah. Then, after you go home, so I allow you to continue to work on 3 selected questions. Okay? Yeah. But not all. Okay? Yeah. 3 selected questions. Yeah. You can redo at home. Okay? Yeah. In that way, reduce your pressure a little bit. Okay? So even you cannot complete the last 3 questions. Don't worry. When you get home, you have time to work on the last 3 questions. Yeah. Things like that. Yeah.
So could we choose which 3 questions?
Right. Yeah. Good question. So last time I did in this way. So I asked students. So I do this way. Okay. Each student you select 3. You give me the numbers. Okay. You write on your test paper. Okay. The top part, so I can see easily. Then I get all of you. I do statistics. Okay. The highest number I select. Okay. Second highest, third highest. Then I base on the statistics. So then I post, those 3 questions. Then you can redo. You can do the second time. Yeah. So last year I did it in this way. Okay. Yeah. Based on that. Yeah. So you have influence. Yeah. But I will base on the feedback from the whole class to choose those 3 questions. Yeah. All right. Yeah. Take a break.